Hi, my name is Amirul Fikri bin Muhammad Soffry from EC1101D. So, in this video presentation, my part is going to explain the introduction of related rates, which is the subtopic of application of differentiation. So, let's go. Alright, so before we jump to the related rates, I would like to explain a bit of what are the purposes of differentiation in life, the application of it. So, calculus was originally developed to understand on how the Earth, the planets, the stars move with respect to each other. So basically, differentiation and integration can help us solve many real life problems. We use the derivative to determine the maximum and minimum values of particular function, such as the cost, the strength of an object, amount of material used in the building, the profit and loss in business, which is, I personally think, that crucial for any businessman out there. So derivatives are made in many engineering and science problems, especially when modeling the behavior of moving object. Yeah, so that is pretty much what are the purposes for. Alright, so what is related rates? Related rates problem usually involve two or more variables that change at the same time. Well, possibly at different rates. If we know how the variables are related and how fast one of them is changing, then we can figure out how fast the other one is changing. This usually involve writing an equation relating the two variables and taking the derivative of the equation with respect to time. Implicit differentiation is often used in this related rates problem. These are some of the examples for the related rates problem.
Hello, my name is Dwayne Rodney. I'm from EC1101D. Okay, this is the problem that we choose for the group assessment for MAT183. Now, this is the question. The diagram shows a closed small cylinder can with given radius and height is placed on a large cylinder. The radius and height of the large cylinder given in the diagram. If the surface area of the above cylinder are 700 pi cm square, express H in terms of R. So this is the diagram. This is the solution. First, we must find the surface area for the small cylinder and big cylinder. For the small cylinder, the surface area is 4 pi r square plus 8 pi rh. And the big cylinder is 28 pi r square plus 32 pi rh. And then the next step, we add the area of small cylinder and big cylinder, which is 700 pi equals to 4 pi r square plus 8 pi rh plus 28 pi r square plus 32 pi rh. And then we solve it like this. For this one, we remove the pi and it becomes 32 r square plus 40 pi rh. And then equals to 700 pi. 700 only, the pi already been removed. And then we move the 32 r square to the right, and then we left the h at the left, so it becomes 700 minus 32 r square per 40. So this is the answer for the first question. And then we move to the next question. Shows that the volume of both cylinders are given by 1260 pi r minus 57.6 pi r cube. This also same with the first one. We must find the small volume for the small cylinder and the big cylinder. The small cylinder volume is 8 pi r square h, and the big cylinder is 64 pi r square h. We total up the volume, the volume of the small and the big, so it equal to 72 pi r square h. And then we substitute h equals 700 minus 32 r square per 40 r to the volume, 72 pi r square h, and then it become 50,400 pi r square minus 2,304 pi r power 4 per 40 r. And then we also can separate it like this, and then it become the answer is 1260 pi r minus 57.6 pi r cube. That means the volume from the answer is shown. Okay, maybe this is the last one. Determine r in cm so that the volume is a maximum. Hence, find the maximum volume of both cylinder. The volume is 1260 pi r minus 57.6 pi r cube. So we must find the rate of radius using first derivative, which is dv dr equals to 1260 pi minus 172.8 pi r square. When dv dr equals 0, the 1260 pi minus 172.8 pi r square also equal to 0. Then we move the negative 172.8 pi r square to the right. After that, we left the r square at the right, and then we move the 172.8 pi to the left again. After that, we cut off the pi, so it become 1260 per 172.8 pi. 0.8 equals to r square. So the r is equal to plus minus 2.7. That means the r equal to 2.7. To find the maximum volume, we must using the second derivative, which is d2v dr square for this one. And the answer is negative 345.6 pi r. When r equal to 2.7, d2v dr square equals to negative 345.6 pi times with 2.7, and then it equals to negative 2931.483 less than 0. Volume is maximum when r equal to 2.7. Hence, the maximum volume is equals to 1600 pi. We change the r with 2.7 minus 57.6 pi 2.7 equals to 10,199.1176 cm cube. Okay, that's all from me for the solution and the problem. Thank you.
For the last part in this video, me, Syazwani binti Muhammad Suzian, will conclude what my group mates has explained. Regarding this topic, we learn how to use differentiation rules in solving related rates problem. In addition, we also can apply this calculation in solving the problem in our real life. For example, calculating the time taken for a snowball melting, time for a ladder falling to the ground, and when a balloon is being blown up. Once we understand the concept of this topic, we could find the rate changes in a quantity by relating to other quantities whose rates of change are known. I hope By showing the example in the previous part of our video, some will gain more knowledge and understand more about the differentiation topic. So that is all from us. Thank you.